In the Why PAM4 video, we discussed both analog and DSP-based PAM4 series, but we did not discuss too much why we need the analog PAM4 receiver, especially recently. More and more people may still work on the analog PAM4 topology. Perhaps we need to let you know that the reasons are, before talking about the analog-based PAM4 receiver RX, we need to make a clear definition of the analog RX, no matter the NRZ, PAM4, or other modulation. Let's start with a simple NRZ RX we are familiar with. As you can see, the input differential data stream of the NRZ RX may have two levels relative to the voltage reference equals 0 volt or ground level. Therefore, we can convert the RX input levels greater than 0 or less than 0 to digital bitstream by a single comparator. It's also called quantizer, slicer, or sampler, which is equivalent to a 1-bit ADC. Therefore, the RX can convert the analog signal to digital bitstream easily after a few steps of analog signal processing without a complicated digital signal processing DSP. Think about the analog signal processing image for 5 seconds. Bingo! The first analog signal processing is to improve the signal integrity at high speed through the analog filter CTOE and approximate IR filter, also partially in the analog domain. Then, the second analog signal processing image is to optimize the sampling phase for the comparator equivalent 1-bit ADC to convert to the digital data with little bit array. In the top level point of view, no matter we perform the analog filter loop or the clock data recovery loop in the analog domain before converting to the digital level. Therefore, we could say this is an analog-based NRZ RX. However, this NRZ topology is 99.99% people used without exception, so no one call that. How about the PAM4 RX? Think about the comparator level image for 5 seconds. Correct. In NRZ, there are 2 levels along with 1 reference over comparator to design for 1-bit conversion. If we have 4 levels in a PAM4 signaling, there are 4 levels along with 3 reference levels to design for 2-bit conversion, which we can extend easily by just adding 2 more comparators. Therefore, from NRZ RX to PAM4 RX, if we just keep the same analog signaling processing at the RX front end by changing or adding the number of comparators from 1 to 3, which is also equivalent to 2-bit ADC in the PAM4 RX data conversion. Alright, what's the advantage of doing the same analog-based RX from NRZ to PAM4? Think about the analog signal processing image one more time. Great. Starting from a high-level view, as you can see, the good thing between the left NRZ RX and right PAM4 RX is that the front-end topology in CTOE, DFE, CDR are almost the same. Then we could implement the analog PAM4 RX using a relatively simple and cost-effective analog circuit design compared to complex DSP solutions. This allows us to have flexibility in either upgrading the NRZ to the PAM4 or downgrading the PAM4 NRZ easily. If you are the CEO, CTO, VP, or just a project manager, what should be the big win for you by choosing the analog PAM4? Bingo! Low cost. First, this analog PAM4X is more economical choice than the DSP-based PAM4X for high-volume applications, where cost or design resource is a significant factor. Owing to its simplicity, you don't need to hire many ADC and DSP-related engineers to deal with the DSP-based PAM4X, which could be roughly greater than 10x the size of the analog PAM4X team. Second, we can shorten the time to market effectively owing to a less capacity in the analog-based X. Third, the simplicity of the analog X can lead to a smaller chip area, lower component count, and potentially lower manufacturing cost. Fourth, we can stay in a low-cost process node in 28 nanometer or 12 nanometer, not a super expensive advanced technology like 5 nanometer. If we have chosen the analog PAM4X owing to its simpler architecture. For example, analog X is relatively simpler than the digital X, which typically involves complex ADCs, DSP, and associated control logic in a high demand of very advanced technology, for example 5 nanometer. Besides low cost, what's another benefit of the analog PAM4X? Think about the PPA images for 5 seconds. Yes, we've just mentioned the low area benefits owing to fewer circuit blocks. Similarly, the analog X typically consume less power than the digital blocks owing to a simpler topology, or does not require power-hungry DSP blocks. In addition, there's no high-speed ADCs and complex DSP algorithms in the analog X to achieve a lower overall power. Furthermore, the low power advantage would also help the PAM4X be suitable for power-constrained applications and have a long-term reliability with less aging stress than the higher self-heating of a high-power DSP-X, which may degrade the performance over time. Therefore, it's not practical to see much DSP-X used in an old technology node, since the power was too much. Instead, the DSP-X may need a very advanced node down to 5 nanometer or 3 nanometer to lower the power, but the wafer cost is too much. Besides the low power and low area, what's more for high performance in the analog PAM4X? Think about the white DFE image when you have the bumpy channel for 5 seconds. Right, the discrete time feed-forward equalizer FFE by FIR can equalize the bumpy channel frequency response better than the CTOE does, which is also the DFE through IRR advantage. In the time domain, those bumpy response will translate to discontinuity or reflection at the channel interface. As shown here, the output after the channel, the RSI or the reflection will be 3 UI, 6 UI, 9 UI, and 12 UI delay, which is not like a continuous long tail from a smooth, lossy, low-pass response. Under such high reflective channel image, the time domain pulse response image might not only show you the non-zero ISI at 11 UI delay, but also a noticeable big ISI at 30 UI delay. From these two time domain reflection images, we can either implement the whole 32 tab DFE or partial floating tab DFE for maximum 32 tab ability. Unfortunately, such larger DFE tabs for highly effective channel is nearly impossible to meet the DFE digital timing in DSP. Alright, what's other high performance in the analog PAM4 RX? Think about the delay or latency image for 5 seconds. Correct. Analog RX should have lower latency compared to the digital RX. First, there's no timing consuming analog to digital conversion at the front end. Second, there's no subsequent digital signal processing running in the low-speed digital clocking, which slow down because of a longer clock period and require multiple clock cycles. The reduced latency for the data path will then benefit for applications requires real-time data processing, such as high-frequency trading (HFT), industrial control and monitor, self-driving automobile, HPC, AI, and other low-latency communication systems. Besides the data latency, think about the clock latency of the RX. Bingo! The low latency in the RX clocking of the clock and data recovery CDR would improve the jitter tolerance in a higher tracking bandwidth, or also reduce the jitter peaking in a greater stability. The analog RX CDR can have better jitter performance and fewer timing errors than the digital CDR. Since the analog CDR does not suffer from the quantization noise and timing uncertainty introduced by the ADC and digital processing. Here are the summarized images showing why we need the analog PAM4 receiver RX. Before the PPA discussion, everything is cost-driven. After talking to several CEOs, VP, CTO level managers to develop a complicated DSP PAM4 RX, we may need to hire a much bigger team than developing the simple analog PAM4 RX. Either the R&D cost or time to market delay is very expensive. Furthermore, the production cost of analog PAM4 RX is relatively cheap by using a relatively simpler design than a complex DSP in expensive process node, 5nm or 3nm. Moving to the PPA. First, the analog PAM4 RX achieves much fewer data and clock latency. The reduced data latency helps application of any real-time data processing, such as high-frequency trading or other low-latency communication systems. The reduced clock latency in the RX CDR helps improve the jitter tolerance in higher tracking bandwidth, and also reduce the jitter peaking in a greater stability. Owing to the simple analog processing in the DFE, a long tap of the DFE can help equalize the bumpy channel frequency response, equivalently discontinuity or reflection easy, which the DSP PAM4 RX cannot do with the digital DFE. Second, low power. The analog PAM4 RX can achieve lower power with a reasonable SNR than the DSP-based PAM4 RX because both high-speed ADCs and compressed DSP are not needed. Third, a simple 2-bit ADC reduces both the analog digital complexity a lot, and the area is much smaller than the DSP-based PAM4RX. In summary, we must have a choice between analog and DSP PAM4RX based on trade-offs between power consumption, performance complexity, and cost, depending on the specific application's requirements. Thanks for watching for the video. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and appreciate your comments down below. Whenever you are convenient, please share the video link with people who may benefit from the videos.